Dear students, welcome to our second part of the lesson on model-driven software engineering. The model-driven architecture, MDA, is a framework for software development defined by the Object Management Group, OMG. Key to MDA is the importance of models in the software development process. Within MDA, the software development process is driven by the activity of modeling your software system. MDA originates from formal systems development, since models are intrinsically meant to be well-structured and well-formed. The overall idea of MDA is to turn non-executable models into executable code. This transformation is supposed to be automatic or semi-automatic, with the transformation code to be the most valuable product of the overall activity. This transformation is also formal, so the verification that the output behaves itself as it was prescribed in the input is increasingly important. The key contribution of MDA to the software engineering field is that transformations are automatic or partially automatic. However, to make them automatic, a machine or a computer has to understand and be able to interpret the models that it uses as an input. As it is widely known, user requirements are neither well-structured nor well-formed, so they cannot be considered as formal. The formalization starts in the later stages, for example, at the design and analysis stage. The initial models described in MDA are platform-independent and platform-specific. The first model that MDA defines is a model with the high level of abstraction that is independent of any implementation technology. This is called a platform-independent model, or a PIM. A PIM describes a software system that supports some business. Within a PIM, the system is modeled with the viewpoint of how it best supports the business. Whether a system will be implemented on a mainframe with the relational database or on an AGB application server plays no role in a PIM. In the next step, the PIM is transformed into one or more platform-specific models, or PSMs. A PSM is tailored to specify your system in terms of the implementation constructs that are available in one specific implementation technology. For example, an AGB PSM is a model of the system in terms of AGB structures. It typically contains AGB-specific terms like home interface, entity bin, session bin, and so on. A relational database PSM includes terms like table, column, foreign key, and so on. It is clear that a PSM will only make sense to a developer who has knowledge about the specific platform. A PIM is transformed into one or more PSMs. For each specific technology platform, a separate PSM is generated. Most of the systems today span several technologies. Therefore, it is common to have many PSMs with one PIM. The final step in the development is the transformation of each PSM to code. Because a PSM fits a technology rather closely, this transformation is relatively straightforward. Agile software development process was offered by Agile Alliance. Agile methods universally rely on an iterative approach to software specification, development and delivery, and were designed primarily to support business application development where the system requirements usually changed rapidly during the development process. They are intended to deliver working software quickly to customers, who can then propose a new and changed requirements to be included in the later iterations of the system. The rationale behind Agile paradigm is that software production is a creative activity, so the overall quality of software depends on the creativity of people. Other nuances are less important. Agile developers are in continuous interaction with domain experts. However, the philosophy of being agile alleviates the need for signing a formal contract for the entire product. Consequently, agile methods have to rely on contracts where the customer pays for the time required for system development, rather than the development of a specific set of requirements. So long as all goes well, this benefits both the customer and the developer. However, If problems arise, there may be difficult disputes over who is to blame and who should pay for the extra time and resources required to resolve the problems. All methods have limits, and agile methods are only suitable for some types of system development. In our view, they are best suited to the development of small or medium-sized business systems and personal computer products. They are not well suited to large-scale systems development with the development teams in different places and where there may be complex interactions with other hardware or software systems. Nor should agile methods be used for critical systems development, where a detailed analysis of all of the system requirements is necessary to understand their safety or security implications. So the software development lifecycle is traditionally comprised of the following 7 phases that you see on this slide. During the first 2 phases, planning, requirements, and analysis, all the relevant information is collected from the customer to develop a product as per their expectations. Any ambiguities must be resolved in this phase only. Business analyst and project manager set up a meeting with the customer to gather all the information like what the customer wants to build, who will be the end user, what is the purpose of the product. Before building a product, a core understanding or knowledge of the product is very important. In the design phase, the requirement gathered in the software requirement specification (SRS) document is used as an input and software architecture is derived. Implementation coding starts once the developer gets the design document. The software design is translated into source code. All the components of the software are implemented in this phase. Testing starts once the coding is complete and the modules are released for testing. In this phase, the developed software is tested thoroughly and any defects found are assigned to developers to get them fixed. Retesting is done until the point at which the software is as per the customer's expectations. Testers refer SRS documents to make sure that the software is as per the customer's standard. Once the product is tested, it is deployed in the production environment. If the customer finds the application as expected, then sign-off is provided by the customer to go live. After the development of a product on the production environment, maintenance of the product, if any issue comes up and needs to be fixed or any enhancement is to be done, is taken care by the developers. Waterfall model is the very first model that is used in software development lifecycle. It is also known as the linear sequential model. In this model, the outcome of one phase is the input for the next phase. Development of the next phase starts only when the previous phase is complete. First, requirement gathering and analysis is done. Once the requirement is frozen, then only the system design can start. Herein, the SRS document in the form of text and diagrams is created and represents the output for the requirement phase, and it acts as an input for the system design. Sometimes requirements and analysis are seen as separate phases, but it doesn't change the whole process, and design always starts when the requirements and analysis phases are completely frozen. In the system design, software architecture and design, documents which act as an input for the next phase are created, that is implementation and coding. In the implementation phase, coding is done and the software developed is the input for the next phase, that is testing. In the testing phase, the developed code is tested thoroughly to detect the defects in the software. Defects are logged into the defect tracking tool and are retested once fixed. Bug logging, retest, regression testing goes on until the time the software is in the go-live state. In the deployment phase, the developed code is moved into production after the sign-off is given by the customer. Any issues in the production environment are resolved by the developers which come under maintenance. The requirements for a system are the descriptions of the services that a system should provide and the constraints on its operation. These requirements reflect the needs of customers for a system that serves a certain purpose, such as controlling a device, placing an order, or finding information. The process of finding out and analyzing, documenting, and checking these services and constraints is called requirements engineering. The term requirement is not used consistently in the software industry. In some cases, a requirement is simply a high-level, abstract statement of a service that a system should provide or a constraint on a system. At the other extreme, it is a detailed, formal definition of a system function. Normally, users do not know what the software should do, however, they can tell what they want as a result. In real life, when requirements are formulated, they are not precise nor complete. They also can contain overlaps and contradictions. Some of the problems that arise during the requirements engineering process are a result of failing to make a clear separation between these different levels of description. Developers distinguish between them by using the term user requirements to mean the high-level abstract requirements and system requirements to mean the detailed description of what the system should do. User requirements and system requirements may be defined as follows. User requirements are statements in a natural language plus diagrams of what services the system is expected to provide to system users and the constraints under which it must operate. The user requirements may vary from broad statements of the system features required to detailed, precise descriptions of the system functionality. On the other hand, system requirements are more detailed descriptions of the software system's functions, services, and operational constraints. The system requirements document, sometimes called a functional specification, should define exactly what is to be implemented. It may be part of the contract between the system buyer and the software developers. Let's look at the example of user requirements. IETU registrar shall keep track of all data related to students' registration and other important information to maintain the university's registering database. System requirements are more detailed and technical. Please take a look at the following example. On making a request for a document from IETU registrar, the requester shall be presented with the form that records details of the user and the request made. IETU registrar request forms shall be stored on the system for 5 years from the date of the request. IETU registrar shall maintain a log of all requests that have been made to the system. In this slide, you can see for whom different types of requirements can be useful and meaningful. User requirements are used by client managers, system end users, client engineers, contractor managers, and system architects. System requirements are used by system end users, client engineers, system architects, and software developers. Software system requirements are often classified as functional, non-functional requirements or domain requirements. Functional requirements are statements of services that system should provide, how the system should react to particular inputs, and how the system should behave in particular situations. In some cases, the functional requirements may also explicitly state what the system should not do. Non-functional requirements are constraints on the services or functions offered by the system. They include timing constraints, constraints on the development process, and constraints imposed by standards. Non-functional requirements often apply to the system as a whole, rather than individual system features or services. Domain requirements. These are requirements that come from the application domain of the system and that reflect characteristics and constraints of that domain. They may be functional or non-functional requirements. In reality, the distinction between different types of requirements is not as clear-cut as these simple definitions suggest. A user requirement concerned with security, such as a statement limiting access to authorized users, may appear to be a non-functional requirement. However, when developed in more detail, this requirement may generate other requirements that are clearly functional, such as the need to include user authentication facilities in the system. This shows that requirements are not independent and that one requirement often generates or constrains other requirements. The system requirements therefore do not just specify the services or the features of the system that are required. They also specify the necessary functionality to ensure that these services or features are delivered effectively. The user requirements for a system should describe the functional and non-functional requirements so that they are understandable by system users without detailed technical knowledge. They should only specify the external behavior of the system and should avoid, as far as possible, system design characteristics. Consequently, if you are writing user requirements, you should not use software jargon, structured notations, or formal notations, or describe the requirement by describing the system implementation. You should write user requirements in simple language with simple tables and forms and intuitive diagrams. However, various problems can arise when requirements are written in natural language sentences in a text document. First, lack of clarity. It is sometimes difficult to use language in a precise and unambiguous way without making the document wordy and difficult to read. Second, requirements confusion. Functional requirements, non-functional requirements, system goals, and design information may not be clearly distinguished. Third, requirements amalgamation. Several different requirements may be expressed together as a single requirement. Let's take a look at an example of a potential problem within user requirements. IITU Registrar shall provide a financial accounting system that maintains records of all tuition payments made by students of the university. System managers may configure this system so that students with GPA higher than 3.5 may receive waivers or discounts. This requirement includes both conceptual and detailed information. It expresses the concept that there should be an accounting system as an inherent part of IITU Registrar. However, it also includes the detail that the accounting system should support discounts for regular IITU Registrar users with certain GPAs. This detail would have been better left to the system requirement specification. Another example for describing functionality for grid facilities, but here too, you can find mixing of different types of requirements. To assist in the positioning of entities on a diagram, the user may turn on a grid in either centimeters or inches via an option on the control panel. Initially, the grid is off. The grid may be turned on and off at any time during an editing session and can be toggled between inches and centimeters at any time. A grid option will be provided on the reduce to fit view, but the number of grid lines shown will be reduced to avoid filling the smaller diagram with grid lines. User requirements that include too much information constrain the freedom of the system developer to provide innovative solutions to user problems and are difficult to understand. The user requirement should simply focus on the key facilities to be provided. In this slide, you can see a rewritten version of the editor grid requirement to focus only on the essential system features. Whenever possible, it is useful to try to associate a rationale with each user requirement. The rationale should explain why the requirement has been included and is particularly useful when requirements are changed. To minimize misunderstandings when writing user requirements, it is highly recommended that you follow some simple guidelines. First, invent a standard format and ensure that all requirement definitions adhere to that format. Standardizing the format makes omissions less likely and requirements easier to check. The useful format people use shows the initial requirement in boldface, including a statement of rationale with each user requirement and a reference to the more detailed system requirement specification. You can also include information on who proposed the requirement source, so that you know whom to consult if the requirement has to be changed. Second, use language consistently. You should always distinguish between mandatory and desirable requirements. Mandatory requirements are requirements that the system must support and are usually written using the word shall. Desirable requirements are not essential and are written using the word should. Third, use text highlighting, bold, italic, or color, to pick out key parts of the requirement. Fourth, avoid as far as possible the use of computer jargon. Inevitably, however, detailed technical terms will creep into the user requirements. System requirements are expanded versions of the user requirements that are used by software engineers as the starting point for the system design. They add detail and explain how the user requirements should be provided by the system. They may be used as part of the contract for the implementation of the system and should therefore be a complete and consistent specification of the whole system. Ideally, the system requirements should simply describe the external behavior of the system and its operational constraints. They should not be concerned with how the system should be designed or implemented. However, at the level of detail required to completely specify a complex software system, it is impossible in practice to exclude all design information. There are several reasons for this. First, you may have to design an initial architecture of the system to help structure the requirement specification. The system requirements are organized according to the different subsystems that make up the system. This architectural definition is essential if you want to reuse software components when implementing the system. Second, in most cases, systems must operate with other existing systems. These constrain the design, and these constraints impose requirements on the new system. Third, the use of a specific architecture to satisfy non-functional requirements may be necessary. An external regulator who needs to certify that the system is safe may specify that the architectural design that has already been certified be used. Natural language is often used to write system requirement specifications as well as user requirements. However, because system requirements are more detailed than user requirements, natural language specifications can be confusing and hard to understand. For many reasons, requirement specifications written in natural language are prone to misunderstandings. These are often not discovered until later phases of the software process and may then be very expensive to resolve. It is essential to write user requirements in a language that non-specialists can understand. However, you can write system requirements in more specialized notations shown on this slide. These include stylized, structured natural language, graphical models of the requirements, such as use case, to formal mathematical specifications. To recap, today we have briefly covered such topics as model-driven architecture, agile development, traditional software development lifecycle, user and system requirements, functional, non-functional, and domain requirements, user requirements and their problems, system requirements, their problems, and notations used for specifying requirements. Thank you, and I will see you in our next class.